So today we are going to talk about, you remember, I think in the previous also set of slides, we were discussing the Caesar cipher, right? So what does the Caesar cipher do? It's a substitution. It's one method of encryption using substitution. And the way it works is you have a key. The key is just a number that tells you for any letter of the alphabet, how much you shift up or down to replace that letter. And it's a fixed shift. So the letter A, if it's replaced by the three letters after it, the one letter 3 positions after it, so the same will happen to the letter X, the same will happen to the letter B, the same will happen to the letter L. Every one of them from the plain text message is going to be replaced by the letters 3 steps away from it up in the alphabet, okay? That's Caesar cipher, and we mentioned that even though it was strong at the time it was created, but that cipher, because of the fact that it uses a very short key, right, it can be broken even with brute force. So how many trials, if you are talking about the alphabets of the English language, how many trials you need to do to try all possible keys? 26. Only 26, right? So you will try that the letter stays the same. No, I'm not getting English language representation. So the letter shifts by 1, and then you decipher the message. You find that it doesn't make sense yet. 2, 3, until at some point you see actual English words. You stop and you know that this is your key,
but
right?
This is only if you know the language it's being.
Of course. So we mentioned that also last time. So you have to have some background information, at least knowing that this is English, this is an image, this is a text, this is whatever, okay? So you need to know some information about the nature of the data being sent across the channel, okay?
And we will be doing this for every letter, no?
Yes. So it's one by one.
So 26, 26, 26, till we get the whole picture?
Yeah, but you do it for all of them at once. If it's a shift by 1, you go for all of them and shift by 1 and see how it looks like, right? Shift by 2, shift by 3 until you get something that makes sense, okay? So that's the Caesar cipher, and I think we discussed also a more generalized version of that, right? No, it's what we will discuss today, okay? So notice that the Caesar cipher treats the encryption letter by letter, or alphabet by alphabet, right? So each one of them, you apply the substitution to it. You don't do it on a group of letters, okay? Any cipher that works on the transmitted messages, letter by letter or message by message, not as a group of messages, okay, in terms of how you do the encryption, is called a monoalphabetic cipher, because it does the transformation from one letter to a corresponding one, from one letter to a corresponding one, and so on, okay? Now, there is another more generalized way than the Caesar cipher to do the same idea, which is a monoalphabetic mapping from a plain text to a cipher text, by simply choosing an arbitrarily rearrangement of the letters. What do I mean by that? I mean by that something like, what we see here is not a good example, because this looks like a fixed shift still. So A becomes D, B becomes E, C becomes F. But let's say, for example, I decided that A, okay, B, C, D, and I will put dots because I cannot go through the 26 ones, okay? So I decided that A is going to be replaced by X, just arbitrarily. That's my decision. That's the key. B is going to be replaced by L. C is going to be replaced by A. D is going to be replaced by Y. So you see there is no exact reason why. It's just one-to-one mapping, okay? And I apply this to all the 26 letters. There's no repetitions, of course. So each letter is uniquely replaced by another unique letter, okay? Now in this case, I've created a cipher as well. And the key in this case is this whole thing, right? This is my key. It shows what is the replacement of each letter. Or you can think of it in a simpler way, that it is actually this row only. Because I will know from the arrangement of the row that the first one is the replacement of the A, the second one is replacement of B, this is replacement of C, D, E, F, and so on, right? So if I arrange them in one line or one after the other, it's known that the first one is replacement of the first letter in the alphabet, the second is in replacement of the second, and so on. So this becomes your key, right? This 26 particular arrangement of letter becomes your key. Okay? And you have to share that with the receiver somehow, so the receiver can decipher the information that you are sending. In this case, how many possible different keys you have?
Same number of the letters.
Only? In how many ways you can rearrange n elements?
26 for 26.
2 to 26.
اشمعنى 2? It's rearrangements, so it has nothing to do with 2. 2 we use it for binaries. Here we talk about 26 letters, right?
So every one will have 26 possibilities.
Okay.
So 26.
But after you put it, the next one will have only 25 possibilities. And then the next one. So this is called what? أيوة. So the way of rearranging n elements, right, is using the number of ways that you can rearrange n elements is equal to n factorial, right? You studied that in your probability and statistics course, online or in class. Half of it was in class, half of it was online. For some of you, not for all of you. Okay? So, so how many keys are there? In this case, we are talking about 26 factorial, right? This makes the key space much larger. And if I am someone who's trying to break that cipher, trying to figure out what's the key, I have to do how many trials? 26 factorial trials. In fact, practically, on the average, I will have to do half of that number. Still, why half of that number? Because sometimes I will find the key very early, sometimes it will take me until the last trial, right? That happens when you are searching over, for example, pages of your book, and you are searching across a book of 100 pages, where you have something written in one of the pages, right? Sometimes you open first, second, oh, in the third page, here it is. Sometimes until you reach page 99, and then you find, oh, I had to count until 99 until I found it, right? So the average is gonna be between finding it the first time until finding it the last time, the average is gonna be in the middle. So that's the total number of possibilities divided by 2, on average, okay? So here we have 26 factorial, right? Which is something like this number that we see here, okay? And you divide this by 2, okay? These are the possible keys. The average number of searches that you have to do until you find the key is gonna be half of that, okay? That's still a very, very big number, 10 to the power 26, right? So like 1 and 26 zeros in front of it. And with any computational capability that you have, this is gonna take a very long time. So brute force attack is not gonna work in this case, okay? Because it requires really very long time until you find the key, okay? So what is the attack that you can perform in this case? This is the idea, or starting from this point came the idea of something called crypt analysis. Crypt analysis is the idea that, again, knowing the language being used in communication, any language has certain statistical properties. So for example, in the English language, the most repeated letter is the letter E, right? That's, if you do statistics of all English words, you will find that the letter E appears approximately something like 13% of the time. According to, across all the words possible in English, you will find that in 13% of the words, you will have the letter E appearing, okay? And then the next one is the letter T. It appears approximately about 11 to 12% of the time. And then after that, the letter A, and so on, right? So each letter in a particular language has its own characteristics of frequency of appearing in any long repetitions of words, or long words coming one after the other. They don't have to be the same words, right? Okay, so this means what? If my message is being encrypted on a one-to-one correspondence, right? For example, the example here. So let's say I move on, and let's say the letter T, for example, is replaced by M, and the letter, we said what, E, B, C, D, E is replaced by K. Okay? Yeah, exactly. I can demap things. So I know that this is English. What I will have is combinations of these, right? Appearing as text or messages going cipher messages, right? I have those cipher messages. I will collect a good number of them. I'll keep listening to the medium, collecting the cipher messages, and then I will arrange them as letters, right? And try to plot statistics. So I collected, for example, 1 million letters, okay, of transmissions, okay? Then I will arrange them and see out of the 1 million, how many times each one of those letters appeared, right? And then I will find that the highest one appearing was letter K. Immediately, if I know that this is English, I will say this must be the encoding for E, because E is the most frequent, right? And they are trying to communicate English messages, but they encrypted it, and according to the encryption, every E was replaced by a K. So if K is appearing a lot, it means it must have been the replacement of E. Similarly, I will find that the next appearing one was, for example, M. So I will know immediately that this most probably represents T, right? Can I have some errors in doing this? Yes, it depends on how many messages I collected, what are the type of the words that they did. But again, even if I have that, I will try, whenever I get a probable key, I will try it. And then I will say, okay, the things that are close to each other, try to swap them. So maybe what I thought is an E is probably a T, and what I thought is a T is probably an E. So swap them, and I'll keep doing some of those fine-tuning trials, not many of them to do. Eventually, I will find English language appearing, then I know that I figured out the key, okay? This approach, there's no brute force here. All I did is collect a large number of cipher messages and then do statistical analysis on them. With the background of the language being used, I will be able to figure out what they were mapping. And then I will find out the key, right? This statistical approach can work almost with any cipher that uses monoalphabetic, regardless of the method. So starting from the Caesar, which is the simplest, going through the most complicated one that we have here, which is the one that does just some random unknown mapping, only known by the transmission and the reception side. In both cases, using crypt analysis is going to get you the key after few trials within a very short time. Okay? Clear? Any questions about this? Okay. The next slide is showing you this particular analysis thing and how it looks like in the English language. So you see the letter E spiking up there. The next one is the letter T. It's actually much smaller than what I said. So E was close to 12.7, that's close to 13%. But T, for example, was at 9% and so on, okay? And for different languages, you will have different statistics. By the way, you can actually enhance your detection by not only doing statistics for single letters, there are also what we can call duetto. So there are two letters that appear a lot with each other. T and H, for example, right? Because they appear in this, that, so, thing, and so on. So TH always appear a lot together. Not always, but appear a lot together. So you can go across again the letters and do them in twos. This and that, this and that, this and that, and so on, and see the repetitions. And once you get a particular spiking repetition, you know that this is, for example, the TH, okay? So you can do also second order, third order statistics, fourth order statistics. Up to that, it's okay. If you go to much higher, it will become useless after a while, okay? So there are ways to enhance this crypt analysis approach, and it has been extensively used to break ciphers in the past before we move to a more advanced cipher techniques, okay? So how do you, those ones that I mentioned, which is like duettos and triples and so on, they are called digram and trigram, okay? What are the countermeasures to break the, to prevent breaking your code using crypt analysis? The only way is to start working on mapping a large string of letters to another large string of letters. So your mapping is no longer one-to-one. Like, for example, whenever I get this combination of letters, X, A, M, T, for example, it's always going to be replaced by L, Z, Q, H, whatever, okay? And at the same time, if I get this, okay, this whole thing is going to be replaced by P, N, T, O. Okay? The replacement here is 4 and 4. It's not 1 to 1. So you can see, for example, that the letter M here was replaced in this 4 to 4 by Q, right? While here it was replaced actually by P. There's no relation. 1 to 1, there is no relation anymore. Okay? I take a block and I replace it by another block, not 1 to 1 way. Okay?
Like if we want to cipher using, for example, ASCII table that has much more components than regular alphabets. So is that still 1 to 1? And we have
It
more
is,
combinations.
you have more letters, so this increases the space that you are trying to cipher, right? But it's still 1 to 1. So you take every ASCII, you replace it by a certain corresponding ASCII, 1 to 1. If you do it by few of the letters together are going to be replaced by few of the letters, and there is no 1 to 1 correspondence, then in that case you hide the statistics of the language. Okay? So no matter how many alphabets you have, that's when you go to the ASCII, it's more alphabets.
Yes.
But if you still map them 1 to 1, 1 to 1, it's going to be broken by the crypt analysis. Okay? So again, the idea here is there is no 1 to 1 mapping at all. I just chose that those 4 are always going to be represented by those 4. And those 4 are always going to be represented by those 4. It's a block by block, right? That's the concept of block cipher. And this is why I said that in the case of block cipher, you get better security, because by default, block cipher, if you choose large enough the size of the block, you are immune to the crypt analytic approach, right? You can be broken using other approaches, but not the crypt analysis approach, because now you hide the statistics of the language, right? Okay.
But doctor, I didn't get it. Yani, the message will exactly be X, A, and T. And they will be together.
Yeah, that's the message that I want to encrypt. Now you don't have to encrypt it word by word, which is like an English word. You probably do few letters, and if you do that with fixed size, then you probably cross the boundaries of the words. So you end up with some letters that doesn't look like a word. But when you decrypt, you put them next to each other, they will compose the correct sentence, right? Yes.
Doctor, you mentioned that I have to read the million transmitted messages. What if I want to apply it over a part of message or?
You mean for the crypt analysis?
Yeah.
I said you need to read a large number of messages so that you can construct reasonable statistics, right? If I collect only 4 or 5 letters, or even 26 letters, right? I might find that among those letters, unluckily, the letter E appeared only once, and there are many other letters that appears a lot, because I didn't have enough population to sample from, right?
So in this case, it's impossible or it's harder
And
to?
in this case, you will have large errors, so you will not be able to decode correctly. You will not be able to break the code correctly. In any statistical approach, generally speaking, right? If I want to, for example, to infer something about Qatar University, let's say I want to see what is the average age of a second-year student, right? If someone goes across the university and picks only like 10 students who are in the second year, and he calculates the age of those 10 students and takes the average and assumes that this is the average of the age of all the population of Qatar University in the second year, most probably the calculations that he did is going to be way off the reality, right? But if someone goes and samples, for example, 1,000 students in the second year, and he calculates their ages average, the average that person is going to get is going to be very close to the one who's going to go across the 27,000 students of the university and pick the ones that are in the second year, the one who does the true calculation, right? And picks the ones who are in the second year and takes the average of all their ages. Those two, the one who only sampled 1,000 and the one who went across the whole second year population, they will get very close numbers. There might still be some errors, but the errors are going to be small. Because now the person who did the sampling had enough number of samples, so the average is close to the actual average. Okay? Same thing here. If I collect only a small number of letters and try to get statistics out of those, probably my statistics will be way off the reality, right? So I cannot do that. Yes? That's a general rule. Has nothing to do with cipher or anything. If you want to calculate some statistics from actual data, you have to have what they call a sufficient sample data. If it's less than sufficient, it will give you wrong calculations. Okay? Any other questions? All right. Okay, so stemming from the idea that we should not do a one-to-one mapping came the idea of doing a 2x2. Okay, and this, the first trial of this was a cipher done by a British guy. His name is Charles Winston. Okay, and the cipher that he did is called the Playfair cipher. Okay, and this cipher has been used a lot during World War I. That was like the state of the art at that point for the British Army. And even though later on the weaknesses in that cipher were discovered, but it was still strong enough such that when we go to World War II, which was like 20 years later, it was still used by some armies, the Playfair cipher. So how does it work? We define a key. The key in this case is just a word. So in this case, in the example that we will look at here, the word is the word monarchy, for example. Okay? This is the key word that we call it the key of this cipher. Okay? In fact, this is not the full key. This is not what's going to be used as it is to encrypt our message. But once I know this and I follow the methodology correctly, I will be able to construct what's called the key table here for the Playfair cipher. Okay? And once I know the keyword, the key table is going to be unique. For this keyword, the key table is going to always look like what we see here. Okay? So how do we construct that key table, which is 5 by 5? And we are talking here, British guys, so they did this for the English language. English language has how many letters? 26. 5 by 5 will give you how many letters? 25. So there is one letter that you will not be able to cipher, and what they decided is it's going to be the letter IJ. Maybe this is because they appear, I mean the J probably does not appear that much in wars, I don't know the reason. But they decided that in this particular, in a particular location within the key, when you have to put the letter I, you choose, either you put the letter I or the letter J. Okay? And whatever you want to apply to I applies to J. So this means that what you will get when you decipher might have some ambiguity in the words. You always have the possibility that this letter was either an I or a J, but that's a one trial thing, right? So I decipher. If the word still does not make sense, okay, the I's replace them by J's, the words will make sense, or the other way around, right? So it's just one extra step after you decipher, okay? So how do you establish the table? You start by, so remember it's a 5 by 5 table. You start by putting the letters of your keyword one after the other from left to right and from up to down. Okay? So monarchy, M-O-N-A-R-C-H-Y. What if the word that you chose as a keyword has a repeated character? For example, let's say the word was something like this, else, right, where? So now I have many times the letter E appearing. That's the only one repeated, right? So what if this is the case? What if the keyword that I chose had some letter which appears more than one time? You show it, you put it here in the ordering only once. So in this case, if I use this to construct the table, I'll start E, L, S, and then ignore this because I've already included E, W, H, and then ignore this, and then R, right? So E, L, S, W, H, R. Okay? Then after you put the keyword in the way that we mentioned, you go back to the alphabets of the English, the ordered alphabets, exclude from them the letters that you have already used here, right? And put them one after the other in order. So you see here, after we finish the word monarchy, we already used A. So we start, the remaining alphabets will start from B. So I put B. C has appeared already, so it doesn't appear again. D, E, F, G, and then H has appeared, so it doesn't appear. I reach I and J, so this becomes I and J together. K, L, I don't put M because it has been already used in putting the key. P, Q, R is not put here because again appeared up. S, T, U, V, W, X, Y does not appear because it was there, and then Z. Okay? So for a given keyword, the whole key table is going to be something that if you follow this algorithm or this approach correctly, for this keyword it will always look like this. Okay? And what you need to share only with your receiving party is the keyword, because they also know how to construct the rest of the key table. Okay? Okay, we have a key table. What's the next step? I get a plain text message and I need to encrypt it using this key table. Now here is another complicated thing, which is how do you do the encryption? It's not very complicated as soon as you see one example of it or a description with an example of it. So how do you work with the encryption? It does as follows. First of all, you look at your plain text, the first thing, and you perform the operation called insert fillers between repeated letters. Only, remember, here we want to do the encoding every two letters together. Okay, so every two letters are encoded into some corresponding two letters in the cipher text. Okay, you only need to insert the fillers if the two letters are going to appear in the same double. So let me give you an example to clarify this. Assume, for example, that the word that you want to encrypt, the plain text word, was the word balloon. Okay, when you try to break balloon into two words, you will get what? BA, LL in the same two. So L and L appears in the same two, and then OO, and then N, right? And you have one letter at the end, right? So if you want to encrypt this, the rule says BA is fine, so you will do the BA. I have LL, since they are two repeating letters in the same unit. Okay, so I have to insert a filler between them. So you decide the filler and you share it with the receiver. So in this example, the filler was letter X. So I will insert X in between. Right? Yeah, okay. It doesn't mean repetition. It means at the receiver, whenever I receive two units, one of them is X, I'm gonna remove it and go to the next, skip it. Because I know that this was a filler, right? We will see, okay? So BA, and then instead of LL, it will become LX. And what's gonna be the next? LO, right? And then the next ON. So no need to insert any other fillers or any other thing, okay? Because the OO here is no longer in one unit after I insert the filler X, okay? I found that LL is gonna appear in one unit, right? So I had to go back to the word balloon and insert a filler, okay? And then look at this and take it 2 units at a time. When you take it 2 units at a time, what will happen? BA, LX, LO, ON. So the O and O did not appear in the same unit. They were separated. No need for filler in this case. So repeated letters are only replaced by a filler if they appear in the same 2-letter unit. If they don't, no need for a filler.
We apply the first filler and then we check.
And then you check, exactly. And then you do this. Computer-wise, it can be done actually in one step, but manually, yes. Okay. That's step number 1. So replacing repeated letters that appear in one message unit, which is composed of 2 letters, right, with fillers X. Okay. Next step is going to be the encoding using the table. So far we didn't use the table yet. Okay. So now you look at each unit of those. So let's say we ended up with this unit, and we want to encrypt, BA, LX, LO, ON, right? So we look at each one of those and we want to do the encryption. In the case that, let's look at the letter BA. B is here, A is here. They both, the 2 letters in the one unit, they appear in the same column. In that case, the encryption is going to be replace each one of them with the letter right after it in that column. So the B is going to be replaced by an A, and sorry, the A is going to be replaced by a B, and the B is going to be replaced either by I or J. And you choose and you stay constant. So it's always going to be either an I or a J. So you either omit the J or you omit the I. Okay? Okay. And if they appear in the same row, very similar rule applies. If the two letters exist in the same row, then you go for each one of them and you replace it by the one right to it on the same row. What if it was at the end? You assume that the row wraps around. So you replace the D, for example, by the C. So the next one is going to be go to the start, as if it's a circle. Okay? And the same for the column. If you reach the end, then the last letter is going to be replaced by the one next to it, which is the start of the same column above. Okay? This is the first case, the case that the two letters appears either in the same row or in the same column. What if we look at this, LX? So L is here, X is here. What is the rule in this case? You go for the first one, the L, you are looking for replacement. The replacement is going to be the letter on the same row, right? And the column of the other one, you're joining it. So it's going to be replaced by S. What about the X? Apply the same rule. You look for something in the same row of the X, and the column of the other one is going to be the U. So you see that they affect each other, right? The selection is affected by both letters. For each one of them, you pick the letter, you look in its row, and you keep searching until you find the letter in the column of the other unit. For the L, it's the row of the L and the column of the X. And for the X, it's going to be the row of the X and the column of the L. Okay?
Doctor, this table
That's
is
it.
generated based on what? Which word? It's not
This table that we see here is generated based on the word monarchy following a particular rule.
so fixed.
Put the letters of the keyword, and after you finish the letters of the keyword, you go for the remaining alphabets in order.
Yeah, I mean the keyword. It's what? It's the key or what? What is
The key is the keyword, because if you share it with the receiver, they would be able to construct the whole thing here, right? And then use the same rules that we used for encryption to do the decryptions. Okay? Okay. That's it. This is how it works. So you start by, number one, constructing the table using a keyword. Remember that if the keyword has repeated letters, you don't repeat them. You show them only once. And then after you finish the keyword, letters in order, you do all the remaining alphabets in order. The remaining ones only. Okay? And then now you have the table, the encryption and decryption. You start by looking at the plain text message. If it has, when you cut it into two letters at a time, if there are two repeating letters in one unit, you insert filler in that location. You do the segmentation again until you end up with segments that does not have any repeating letters. Okay? Now you take them and you go to the table. If the two letters in the unit that you want to encrypt appear in the same row or the same column, you apply the rule of replace each letter by the one after it in the column or the one after it in the row. Okay? Now, if they appear in two different rows and of course two different columns, okay? So in that case, each one of them is replaced by the letter on its row and the column of the other one. Okay? That's the encryption of the play-phase cipher. Nice. It hides the one, the mono alphabetic. So it hides the statistics of a single letter, but not that much, because it's only composed of two letters. So if you perform crypt analysis on this one, you probably need a little bit more than the mono alphabetic case, but the whole system can be broken again using crypt analysis with a little bit more number of steps. Not that much complicated, and it can still be broken, especially with nowadays computational capabilities. It can be broken like that, okay, in a blink of a second, actually. Okay. Okay. So, break. The next slide is just showing you that many of those, even a couple of them, we will look at them in the next few slides, like the Viginier I think that's how it's pronounced. I'm not 100%. And I think it's spelled incorrectly here. There is an E after the G as well. But anyways, so this is another encryption method. We will discuss it in the next few slides. But all those ones that relies on a single, so monoalphabetic, or even polyalphabetic, so multiple alphabetics in one encryption, like the Playfair and this, the Vigenère Cipher. If the number of combined alphabetics together is still a small number, so 2, 3, 5, then still cryptanalysis is an effective technique that works against those. As you can see, the plots here are showing you if you go to that particular cipher and you order the ciphertext letters from A to Z, the ones that are already encrypted, you will see that the trend still looks like the original language without any cipher, the plain text, which means that you can simply go to this one and you will know that the highest repeated here is going to be equivalent to the highest repeated. The next highest repeated is going to be equivalent to the next highest repeated, and so on. So just by doing cryptanalysis again, you can, with a little bit more errors, but you can resolve them with those swapping actions that you can do. And then after a while, you just break the code, okay? The only case where it will become really useless is if you manage to combine large number of letters together, and then in that case, if you analyze the ciphertext, you will see that almost all the letters are repeated equally. Because intuitively, why this happens when you combine a lot of them together and you do a multi-to-multi mapping, as I mentioned a few slides ago, okay? Because in that case, every letter in the ciphertext has actually the statistics of many other letters from the plain text. So as if you combine the statistics of all the letters or a good number of the letters into one in the ciphertext. So now this is repeated as much as A, B, N, O, and T are repeated. And the next one is in the ciphertext. The B, for example, in the ciphertext is repeated as much as Z, O, T, N, T are repeated, and so on, right? So this means what? The end result is every one of them is going to average out all the repetitions of the other letters. So they will appear in the ciphertext as if all the letters are equally likely to happen. And in that case, you cannot really figure out which one to map back. Okay? So this is why when you combine a large number of letters, you will end up with something that looks like this. And in this case, you can really have something which is immune to cryptanalysis. Now, just to let you know, if something is immune to cryptanalysis, it can still be broken by other methods. So don't be so happy whenever one method of breaking. So we see now, when we increase the key size, the brute force became useless. Now when we do multi-to-multi with a large size of a block, the cryptanalysis is going to be useless, but there are other ways also to break those upcoming systems. And there are always going to be some ways to break the systems, and there are always improvements in the encryption technology to overcome those ways, and then new ones will appear, and then new methods will appear, and they keep running one after the other. Similar to the antivirus game. So I have the antivirus that can detect all the existing virus, and then someone comes up with a new virus, and now I need to update my antivirus to detect the new virus, and then they come up with another one, and so on, right? And I have one way to crack my iPhone, discover a new update for so the company is going to issue a new OS that blocks that way, and then the companies or the guys who work on breaking those are going to invent a new way to break the new OS, and then the new OS is going to come up with another version, and they keep running one after the other. It's going to stay like that, I think, forever, okay? So anyways, so there are other more complicated, so many-to-many mapping methods. One of them is called the Hell cipher, and that's not the hell like the ربنا عافينا يعني the hell, but that's the name of a guy, Lester Hell. He's a mathematician, and he came up with this cipher in 1929. Okay. Nice thing is that in this case, almost the single letter repetitions are hidden. But again, if you do cryptanalysis with double letters, like a digram or a trigram, you can actually eventually break the code. What does he do? He actually uses linear mapping. So we see it actually in the next slide. Every cipher value, like letter or bit, if you work at the bit level, is represented as a linear function of 3 other plain text values. Okay, so this means that the statistics of this is averaging out the statistics of 3 other letters. That's why it's very difficult in this case to do cryptanalysis with 1 letter analysis, but when you go to 2 and 3, you will still be able to find the key eventually. Okay. Again, so this is just an example for 3 possible cipher texts, right? Using 3 possible plain text letters and combining equations. So 3 by 3 linear equation can be always represented by a matrix and a vector representation, right? You know that already. And there are 2 ways to do this. Either you use the vectors here as row vectors, and in this case, it's written on what they call the left multiplication approach. So you say that C is equal to P multiplied by K. If this was a column vector instead of a row, then it would be C is equal to K multiplied by P. So P appears after. If it was a column vector, both representations are equivalent to each other. You can either use the row vector representation or the column vector representation. Okay. Everything here is performed mod. So the arithmetics here, when you do the calculations to figure out the output cipher letter, everything is done mod 26. Why mod 26? Yeah, because imagine that if I do these calculations, I have, for example, here, maybe this number is 1, this number is 2, this number is 1 again, right? Okay. And then the letters that I used were the letter A, which has the value 1, the letter B, the letter X, which has the value 26, 20, 24. And the last letter that I used was the letter C, which has the value 3. So when you multiply and add, what will you get? 1 plus 48, right? 2 times 24 is 48, plus 1 times 3, which is 3. So the total is going to be what? 52. Now 52 is not any of the English alphabets, right? So what do you put? So in order to always map whatever you get into a letter, so it has to be always mapped into a number between 1 and 26. Then in this case, you have to do what? Mod operations, right? So if you take that mod 26, what's going to be the result? 52 mod 26 is equal to 0, because that's the remainder of dividing by 26. And 52 is divisible by 26, so the remainder is 0. So this is equal to 0, and the letters are, in mod 26, the letters should be numbered from 0 to 25. Okay, because the possible numbers are from 0. So that means that it will map to the letter A. That's the one numbered as 0. Then B, 1, 2, 3 until 25. Okay, so this is why they do all the operations mod 26. If it was another language, like the Arabic language, for example, I think we have 28. In some cases, they say 29 because they count lam alif as another letter, but it's not a letter, it's 2 letters. Anyways, so if we have 28 letters, this means all your operations in the Arabic language will be done mod 28, because you want eventually to end with one of the possible Arabic alphabets. Okay. Maybe Russian, I don't know how many letters they have, so it has to be mod the number of letters in the Russian language and so on. Okay. Okay, so those all are called polyalphabetic ciphers. One of them is the Playfair cipher. The other one was the Hell cipher, right? Because we don't map 1 to 1, but we map multiple to multiple. And one of the strongest among those is what's called the Vigenère cipher. And that one is, interestingly speaking, it's a repetition of Caesar cipher. So you perform Caesar cipher multiple times, and that's how you do the Vigenère cipher. So let me describe it in more details. The equation here explains this equation explains how you do the encryption, and the decryption is just simply the opposite. The way it's written here, in my opinion, is very confusing. So let me describe it, and then you will see why it's represented by this equation. Okay? What happens here is that you get a key that describes to you for every letter what's gonna be the shift in the alphabet, right? And that's what you see here. So your key, for example, is gonna be the word, let's say, world wide. Okay, so that's one word, for example, worldwide. Okay. Now this means what? What's the value of the W in the alphabets? I don't remember. So someone has the table or something can. So let's do it. Okay. So Z, X, Y, Z, W, X, Y, Z. So yeah, it should be 22, right? 20 or 21?
23.
23? Y, X, Y, Z. The 26 is Z. 25 is Y. 24, yeah, so 23. Okay. What about O? حد يطلعها من الانترنت ولا حاجة؟
لازم اغنيها.
Oh, 15.
15 هناخد كلامك مصدق. 15. Okay. An R. Okay, it's enough to have two of them. It's enough to have two of them. Okay. So this is your keyword. Okay. And then your plain text is something like this. This was a good trip. Okay, so that's the message that you want to send. Okay, this was a good trip. Okay, so how do you do the encryption? The T has a particular value. The shift of the T is going to be represented by the first letter here of the keyword. So if T for, what's the value for T?
20.
20. Okay, and W is 23, right? So the resulting letter is going to be 20 plus 23, and then you have to do this mod 26. So the result is going to be what?
43.
Yeah, so 43 mod 26 is going to be yeah, what's the 17 exactly? So this is going to be equal to 17. What's the letter at position 17?
Q.
It should be the next one because we did the calculations assuming that the A is 1, not 0. Yeah, so it's
Q صح.
يا ابن الحلال.
Q. خلاص? So this means it's going to be replaced.
15 اللي هي O. BQ. 17 is Q.
يا الأساس كده.
So
Because we count A as 1. We didn't
Yeah.
count A as 0.
Yes, so if you count A as 1, 17 should be Q, right? Yeah, okay. So this, again, you do the same for the next one, you do the same for the next one. So what if you run out of the keyword and you still have letters here? You repeat the keyword again. And you keep repeating the keyword until you finish the encryption. Okay? So the encryption is gonna be that. For each letter, you perform a Caesar, a shift, but the shift from one letter to the other is different. And the amount of the shift is represented by the letter of the keyword. تمام? Clear?
Okay, what if we end up don't having the letters? What if we end up don't having the letter?
Not.
apply the keyword.
You repeat the keyword, ma, this is what I was saying here. You repeat the keyword again. So you finished until, let's say, the A across came with the E. The rest, what will you do with it? You write again world wide, and you keep repeating it until you finish the encryption. Okay? So you keep assuming that the keyword repeats until you no longer need to do anything with it.
Doctor, so for like the letter H, when we H, the position is 8. So 8 minus 15, you get minus 7. So
Yes.
what do you do in that case? You
8 minus, there is no minus. There is always plus. There's no minus here. It's always plus. Okay. Again, minus will give you another way of mapping, but we are always using addition. Okay. Yeah. Okay. So why is this gonna hide the single letter and the multiple letter better than the other ones? Because you can see that depending on the keyword, right? Some letters will map into two different outputs. The same letter can map according to its position in the sentence. It can map to two different letters in the output, right? So for example, let's pick one case here that this will
Yeah,
happen.
but how to decrypt it if it would be like this?
But because you have the keyword and you apply the keyword again at the receiver side, right? With a minus shift. So for each letter, it will bring it back to its original because it uses the keyword, right? But as a result of this operation, you can have the same letter mapped to different letters depending on the keyword, because the keyword defines the mapping, right? So you can see why the operation is written this way. Okay, I can explain to you. So you pick the element number I of the plain text, we call that PI, right? What if the plain text is at a location I which is greater than the size of the keyword? Then you use the new repetition of the keyword, right? This is equivalent to going to the start of the keyword and moving according to how many locations you are away from the end of the keyword, right? This can be represented by the location that you are in right now mod the size of the keyword. This is exactly equivalent to that I repeat the keyword here, I repeat the keyword here, because I'm gonna pick the one that falls in location 2 in the newly repeated keyword, which is exactly equivalent to the mod operation of my current location with respect to the size of the keyword, right? So that's why we have a mod here. And then the whole calculation is gonna give you a number. You need to map it to one of the 26 alphabets. That's why you do another mod 26, the result of the summation or the addition. Okay? صحيح معايا ولا نمتوا؟ طيب.
How to process الموضوع.
صحيح بس البروسيسور واقع. طيب.
دكتور معلش تعيد بس الموديل الأولى شو بتسوي؟
المود الأولى دي أشرحها لك تاني. Let's assume that my keyword is only composed of 4 letters. تمام؟ letter. We are continuing with the Visioneer Cipher. And just a reminder, in this cipher, you had a keyword. For example, the keyword here is deceptive, right? So DECEPTIVE. And then you have the plain text. And the idea here is that you take the value of this letter to do the encryption. You add it to the value of this letter, and then you perform this operation mod 26. The result is gonna be the cipher text, okay? Now, if you run out of the keyword, you keep repeating the keyword again and again and again, okay? So that's how you can encrypt a longer plain text into cipher text, okay? So we did discuss this in details last time. There is some extension to that, which is called the auto key system for the Visioneer encryption or Visioneer cipher. In this case, you actually concatenate the key with the actual text. So you have here your key deceptive. All what you do is you add to it the rest of the key is gonna be picked from the actual cipher text as you go. So deceptive, and then you start where we are discovered, save yourself, right? So you have here, we are discovered, save your, right, up to SAV. That's what you need to finish the length here. This is an extension that allows you to do the ciphering without repeating the keyword over and over again, because this has some advantages in terms of the cipher not being easier to break. But again, even with this extension or this auto key system, still the Vigenère cipher can be broken using crypt analysis, but a little bit harder than the other ones. So even the strongest one that we see here, which is the Vigenère, among all the other polyalphabetic cipher systems, even this strongest one can still be broken using crypt analysis. And I will scroll back, I'll stop the recording and scroll. So when you are trying to break, the question is, how can they know the plain text from the key? That was your question. The direct answer to that is that the inverse of the encryption operation is the decryption or the decipher, right? And how do we do that? If I have the key, if I know the key, right? If I know the key, your question is how they know the plain text from the key. If I know the key and the cipher text is passing in front of me in the communication channel, because the cipher text is being sent out, the encrypted message, right? I can capture that, apply the key to it, I will retrieve the plain text. The whole idea of encryption, decryption in symmetric systems, the same key is used with the encryption function, and also the same key is used with the decryption function, right? So if I know the key, I solved everything. If your question is how they figure out the key using either exhaustive approach or brute force approach, so you try all the possible values for the key until you find some text that makes sense, that's typically in any intelligent modern cipher system, this is very expensive computational. You cannot really do it in a reasonable time with reasonable resources. So the other option, we said that whenever you communicate, your plain text comes from a particular language or from a particular source that has certain characteristics. It's either an image or English language text or something, or voice of a human, right? Those plain sources, they have certain statistical properties, right? And if your ciphering method does not completely hide these statistical properties, you can always read cipher text, analyze it using statistical method, and then figure out that this cipher character repeats the most, and then the other one repeats a little bit less, and then the other one repeats less, and so on. If I go back to my original assumed communication language, let's say English, the highest repeated letter is E, then probably the highest in the cipher, which was X or Z or whatever, is a mapping of the E. So now I know that every E is substituted with an X, and so on, until I figure when I do this, I will establish a key, and then anything that goes in front of me, I will be able to decipher it. Is it clear now? Yeah, okay. Okay. Good question and very important, so you understand where the process comes from. Okay. Now the other cipher is the Vernam cipher. Vernam cipher is just a regular cipher. It uses an operation between a stream of bits or a block of bits and a key which is composed of bits, right? And then the key itself, again, is in this particular case, is just simply XORed with your message. So you have a message which is composed of a block of bits, and you have a key which is a block of bits as well, the cipher key, the encryption key, and then the operation of ciphering is simply XORing. You take those bits of the key, you XOR them with the bits of your message, okay? Now this is not a very strong cipher unless your key is generated every time as a new key whenever you have a new block of bits, right? Remember, what did we call that? Whenever you generate a new key for every single message and you make sure that the key is totally independent from the message? The one-time pad, which was the strongest possible, right? The problem with that, as we mentioned earlier, is that you need to, every time you generate a new key for every message, you need to make sure that somehow this key is conveyed to the receiver side, not through your communication channel, through some other reliable, secure communication method, okay? Practically, this is very difficult, but again, the Vernam is basically dependent on the same concept. Now, for practicality, the Vernam is based on generating a few keywords in a certain sequence and then repeating that sequence over and over again, okay? That's not very much secure because, yeah, it saves you from the problem of having to convey the keys, because there is a deterministic sequence from the start key, and you go and you drive the others automatically if you know the start. So you only need to share the start, and then automatically the transmitter and receiver will be generating the same keys, right? But that's not a one-time pad. If you want to make it really as strong as you want, then you should go for one-time pad. With one-time pad, you will have the problem of how to share the key every time, and that really results in slowing down your system to a very, very slow communication system, right? So you can achieve very high security, and that's what Shannon's measure of security says. You remember when you have a communication channel and a wiretap channel, we used to calculate the capacity of the two channels and the difference between them, between the communication channel, the secure communication channel, and the capacity of the wiretap channel. The difference between those gives you the secure rate that you can achieve. How much you can transmit in terms of data, in terms of the speed or the rate of data, without being broken by the wiretap. You remember that, right? We had always when we had this setup, right? Let's say that this is the eavesdropper. Okay, and okay, we have, this is the secure communication channel. This is the wiretap channel. Okay, and typically we were calculating the rate over this channel. This is the rate of Eve. This is the rate of trusted, right? And the secure transmission rate was equal to the rate of the trusted minus the eavesdropper rate, right? And if that goes to zero, it means theoretically you cannot achieve any secure communication. If this rate is a number greater than zero, then this is the highest bit rate that you can communicate with your receiver without being broken by the eavesdropper. And here we see that if you want to implement the the one-time pad, right, we can understand a little bit where does this measure that Shannon used, and we use it for theoretical measurement of secure communication, where does it come from? Because typically, in order to secure your communication, you need to make sure that you send, first of all, you need to make sure that you generate a key which is as big as your message. Cannot be smaller than the message, otherwise your system is not fully secure, right? Now this means what? To transmit a message, right, you need also to transmit the key. So this means that for every n bits of message, there is an extra n bits of key that needs to be conveyed, right? This means the effective transmission rate is broken down to half, right? Just to keep the security. Not only that, now this communication also has to happen somehow in a very secure channel, which might even slow down the rate further, right? This is why eventually, when we want to communicate securely, we end up with some rate that's smaller than the regular transmission rate between any two parties, right? I can communicate with you because the channel between us allows a communication at 1 megabit per second. Fine. But if I want to make my transmission secure, and there is an eavesdropper who has a transmission rate capability with me, half megabits per second, then I can only communicate to you at half megabit per second to make sure that my communication is secure. If I go above that, if I try to reach the original 1 megabit per second, definitely my communication will not be secure. Why? Because at least I have to share a key, which is gonna slow my communication, right? So the measure itself is a reflection of what happens in practicality. It doesn't show in the derivation, but I'm just telling you that if you do the derivation, we didn't do it because that's a little bit mathematically involved. But the fact that your rate drops when you want to communicate securely comes from the fact that you need to generate keys, share the keys, and those keys have to be at least as long as your message, okay? So because of that extra overhead, your communication capability to be secure has to drop its rate, okay? Just as an explanation where it comes from. Difficulties, we already mentioned them, that generation of random keys and so on. The remember, I think we have been through this earlier, right? So we said that in order to perform ciphering, we have mentioned that earlier, there are two ways to do that operation. The first way is substitution. So you take a particular plain text and you replace it with some cipher text based on some key, right? And this is the operation that we have been looking at when we looked at the Caesar cipher. This is the operation that we looked at when we looked at all the other methods that we have been through, such as the polyalphabetic methods like the Vigenère cipher, and we have been also through the, what was the name of that cipher? Playfair cipher, right? The one that uses a table. In all these cases, right, we were doing what? We were taking your particular or original message and then removing the letters in the original message and replacing them with some other letters that comes from a key, right? So maybe, for example, your message was the word this, but what you will send is going to be X, Y, L, M, right? Completely different letters. Okay? This, whatever the way you do that replacement, the overall result is that your operation is a substitution. You replace a set of letter with another set of letter. Some of them might be the same, some of them might be completely not in the original message, okay? The other way of doing encryption is that you keep all the letters as they are, but you just simply reorder them based on a particular key, right? Now, in that case, the letters are exactly the same, but the ordering will make it impossible for a receiver who doesn't have the key to understand the original message, right? If I send you the word this, right? And then I reorder it such that it looks like this, right? For example, well, sorry for the word, yani, that's not, I didn't mean let's use this, okay? So, I mean, this doesn't mean anything, will be very difficult for you. Again, this is a very small word, but it will be very difficult for you to figure out that the original word was this. There are many possibilities for the original word even, right? In many cases, if you rearrange them, they will make sense. And then rearrange them again, they will make another sense, right? So which one, you wouldn't be able to figure it out unless you have the key. This operation of shifting things around but keeping exactly the same blocks of letters is called a transposition method for encryption. So we have two ways, okay? Either a substitution, so the key tells you which letter replaces which letter, and the value changes, or a transposition, which means that the values of the letters are exactly the same, but I just reorder them in a way which is unknown to an attacker. And the key, sorry?
I cannot apply both.
You cannot, you can. I'm just saying these are the two methods. I didn't say that you have to use one or the other. You can even, this is what we will see actually in more advanced ciphering methods, that they use a combination of both. Because there is an advantage in doing that. We will come to it later, okay? So yes, as you said, we can actually apply both methods if you want. But in terms of categories, there are those two methods, okay?
Doctor, the
Yes.
key here, is it a private key or?
The key is still private. Yeah, so the key here is gonna be what exactly is the rearrangement. We will see one example of encryption using transposition. So let's look at this. It's called the rail fence cipher, okay? The rail fence cipher is a transposition cipher, pure transposition, has no substitution at all. And the way it's done is very simple. You have the plain, so first of all, there is something for this cipher called the depth of the cipher. That word, the depth of the cipher, is a number that tells me how to arrange things such that I can perform the transposition later on, okay? So for example, just to understand how it works, let's take an example. Assume that the plain text message that you want to send using the rail fence cipher is meet me after the toga party, okay? That's the actual plain text message. And I told you that I want you to encrypt this using a rail fence cipher with depth equal to 2. once you got the depth, what you will do is the following, okay? You will start by taking this message and alternatingly taking the first letter, putting it in the first row, second letter goes to the second row, third letter goes to the first row, fourth letter goes to the second row. So you can see M-E-E-T, so meet comes from here, right? Me, after, right? The toga party. Now I arranged them because the depth was 2, then 1, 1, 1, 1, 1, 1. If the depth was 3, then you do it in 3 rows. First letter, second letter, third letter, fourth letter goes back to the first line, fifth letter, sixth letter, seventh letter goes back to the first line, and so on. Okay? So the depth tells you how to do the arrangement. And now all what you need to do is send this and then this. So what you will send is Mima, TRHTGPRY, and so on, right? So after doing that rearrangement, you will just go through the lines one by one from left to right, and you send the text or the letters one after the other. You can see that what I sent is exactly the same letters that I had originally. They are just rearranged in a way. The way here is defined by the key. The key here is simply the depth. All you need to know is what's the depth. So the key is a single number. Okay?
And the depth is the number of the rows?
Yes. So basically it tells you how many letters you have to spread across rows before going back up to the first row again. Okay? So 2 means take the first one in the first row, second in the second row, go back to the first row, second row, first row, second row, and so on. Okay? Yes?
How will the receiver know from which letter he should start the second row? Because now it's like one line.
Yeah, but the receiver is going to perform exactly the same operation. That's it. And then the letters will go back to the correct way. Right? Just reverse this operation and the letters are going to go back. So when you receive this message, right, you will do the following, okay? I will go for first letter and then after a certain time, take this. So that's your question. How would I know where is the other E, right? I will tell you how would you know that. In those encryption methods, you have to know what's the length of the message. So you have to know how the block size. So the block size is going to tell you exactly what you need to do. Either break the message that you receive into 2 halves and then pick them up again, or if the key was 3 and you know the block size, then you break the block size into 3 rows, right? And then you start picking them one after the other. So the block size has to be known to you. Okay? Any other questions?
Can you give us an example of that?
It's right here.
No, I mean how to.
Yeah, again, if you know now that the block size that you are trying to transmit or the message size that you are trying to transmit is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, right? This means immediately, now if it's 23, make it 24, okay? And then start. This means that the first line has to be 12 and the second should be 12, but it's gonna finish one earlier, right? Okay, so you know that you receive this message, you break it into 2 rows. This is what you receive, right? You broke it into 2 rows and then you start picking them up like this. Go here, 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 and keep doing this until you finish. Okay? So by knowing the depth and the message size, you can easily decrypt the system. Okay? There is another way to do, or a more generalized way to do transposition, and that is called the row transposition cipher. So rather than just simply arranging your message in certain number of rows and then going through them one by one, so alternatingly, right? You can actually have a more generalized rearrangement. In that case, you use something called the row transposition cipher. And the row transposition cipher is based on breaking your message into a certain number of rows and a certain number of columns, right? So for example, here we have 1, 2, 3, 4, 5, 6, 7 columns. And we have 1, 2, 3, 4 rows. So the first thing is you define how the block looks like. How many columns, how many rows, okay? And then you put your message sequentially. So attack, postponed, until, attack postponed until, where is the, yeah. Until 2 a.m. XYZ. Okay, so that's the actual message. Attack, and then starting with the P, postponed until here, and then starting with the U, until, and then starting with the T, 2 a.m. XYZ. That's the plain text message. You decided to arrange that in 7 columns and 5 rows. Okay, that's just how you set up your block. There is no encryption yet. And then the key is going to be a sequence of numbers. Each one of them is representing the order of the column. So simply here, it means that you will send this column first because it's number 1. And then you will send this as a second column. You send this letters from up to down as second. And then you will send this as the third. And then you will send this as the fourth, and so on, based on the number that you have here. This is gonna be your key. So the key here is composed of a key length equal to the number of columns in this cipher, okay? And the values inside tells you what's the order of each column. That's the key used for ciphering and deciphering. So you can see here that you start with this one, so TTNA, the first thing being sent, and then the second is APTM, so APTM, and so on. Okay? Clear? At the receiver side, since you know the orders, right, with the same key, you can simply reorder them. Okay? Any questions? How do you simply reorder them, by the way? Yeah. So tell me, you tell me. So what you have at the receiver is this exact same number. When you receive this message, first of all, you are gonna do it what? You are gonna put it in columns again, right? So when you receive this, the first few, like the first 7 are gonna be 1 column. Sorry, the first 5 are gonna be 1 column. The second 5 are gonna be, because you know that the column length is 5, the length of the column, right? And the third is gonna be, and so on. And then above those, these are the cipher ones. So these columns comes from this guy, okay? And then above, you still have those numbers, 4, 3, 1, 2, and so on. So how do you bring them back to their order?
Put them on the rectangular. Like we know that we have 4 rows and 7 columns. We start like putting them on columns and then start to arrange.
So we already put them in columns. خلاص? But we put them in column one after the other, right? Because that's what we have in the message. And then we have the key. What should we do now?
Because we have the plain text already.
Hmm?
Since we have organized the columns as the key, then also we have the plain text.
I'm confused. We organized the columns now as we received them. We didn't yet do anything. Tell me how to organize them using the key. That's my, because if you organize them using the key in the right way, you solve the problem. But my question is, if this is the key, which is exactly this, right? And now you received those and you put them just in columns, right? Now, how do you reorganize them based on the key? How would you do that? Tell me, how? What's your logic?
The first 5 letters, I put them in column 1.
Okay.
And I swap each one according to the numbers. And then
So,
I'll be able to-
so basically, okay, you swap each one according to the number. So you are telling me, for example, that this one, right, which you receive first, and it will have the number 4 above it. What will you do with it? You'll take it to the 4th column.
No, this column will go to the first, like number 1. I will place it under this column.
This column. مش فاهم يعني ايه this column will go to number 1. The text in this column will go to number 1.
Yes.
Okay.
وبعدين بعد الخمسة أحرف الثانية أحطهم تحت رقم 2 وأمشي على
تمام. So you rearrange them such that based on column يعني location here should go to the corresponding number. Yes, that's how it's done. Okay, got it. So when you are trying to figure out the location of this, you don't care about the number above it. You know that it is the first one, so it should go to the location that includes the key value 1. Yes, that's it. Okay, تمام. And the same for all the others. So this is the second one. You look up here, where is the column ordered as second, and you move that to that column, and so on. Okay.
Doctor, how did you know like each row has like 5 ones?
This is a setup. So you decide from the beginning that your communication system has a certain configuration. In that configuration, you decide that the number of columns is going to be this and the number of rows is going to be this. So that's kind of a configuration that has to be agreed upon or configured correctly at the transmitter and the receiver. Okay. Here is just a quick discussion about the fact that when you do transposition with a single step, still there is some kind of an inherent pattern in your system that allows the recovery or the breaking of the key easier than when you do transposition more than one time. So let's look at the example that we visited earlier, right? This is kind of the original locations of the letters, right? So we have here our letters, right, of the plain text. And let's say that we just call them letter number 1 up to letter number 28, okay? And then the question is, if I start doing the first rearrangement, which is simply applying this key to eventually end up with this setup, right? This result comes from applying this key to this original plain text. You end up with this one, right? Agreed? Okay. Now, if I do this and I track the locations of the letters, I will find that, okay, the first letter here was the first letter that appears in my message, was the third letter in the original message. And then the one after it was the 10th letter, and then the 17th, and then the 24th, and then number 4, 11, 18. Do you notice a pattern? So between this one and this one, there is 7, 7, 7, and then I start 7, 7, 7, and then I start 7, 7, 7, and so on, right? So there is a particular pattern in terms of the new locations as opposed to the original locations, okay? This makes existence of such pattern, which is repeatedly happening, makes it easier for an attacker to figure out the relation, okay? Now, if you go and apply the exact same cipher one more time, so after you end up with this, you go and apply to them the same key in terms of rearranging. So you do one more rearrangement using the same key, right? The end result is gonna be that the locations are gonna be as you see here. Very difficult to find a pattern in this case. So 17, letter number 17, followed by letter number 9, followed by letter number 5, followed by 27, followed by 24. There's no pattern. Just, it looks like random, completely random, right? So this is just to tell you that for the row transposition, to make the cipher strong enough, you need to apply it at least twice. Doing it once is gonna give you some pattern that allows, in terms of the locations, that allows an attacker to figure out the key in an easier way, or to decipher your message in an easier way. Last thing that we want to discuss in this part is that in order to hide your information from an attacker to achieve secure communication, there are two general approaches. One approach that we have been studying all the way until now, which is called encryption. So everyone knows that there is a message out there, but they don't know the actual content of the message, right? This behavior is, or this methodology is called the cryptography methodology. There's another methodology to communicate in a way, in a secure way, which has a different philosophy. That philosophy is that you hide your message such that any attacker doesn't know exactly where is your message, or doesn't know even if you are sending some important information. How would you do that? Either by making sure that the attacker cannot listen to it at all, cannot detect that there is a message, okay? By making it, for example, very weak, or the general principle, the word very weak again falls under the general principle of hiding it in a lot of irrelevant stuff, right? So for example, by the way, I don't know exactly where is the hidden message here, but for example, you can assume that all what I wanted to tell the other party is, for example, 2 years proposal, for example, okay? But this message, 2 years proposal, right, was hidden in a big paragraph, okay? Such that any attacker, if he doesn't know that I'm trying to send a message right now, and that attacker is just listening to what's going on, that attacker is gonna read a big paragraph about someone who's greeting George and communicating with him about something related to Oxford, who thanking him for some letter that he has sent before, and so on, right? The idea here is, if the attacker doesn't know in the first place that there is something hidden here, that attacker will not be able to figure out your message in the first place, right? This approach is called steganography. There are many ways to do that. Some of them are physical ways. Remember when we said earlier that what you can do, for example, to make your communication system more secure is that you can send a jamming noise towards the listener, the eavesdropper, while making sure that that noise does not go to your actual receiver. Now, what happens to the listener in this case? The listener will end up with your actual information hidden among some noise, so that listener will not be able to detect your information. Okay? This is a method, not a method of encryption. This is a method, you can put this under the category of steganography. Noise does not have to be really something random. Noise can be a lot of irrelevant information around your actual information, like this case. So there's a lot of information here, but all of that information is irrelevant related to your message, right? And the protection comes from the fact that the attacker doesn't know in the first place that there is a hidden message here, right? In the case of cryptography, the attacker knows that there is something being communicated and it is important, but he or she cannot read it because it's encrypted, right? So that tells you that these two different approaches have two completely different philosophies, okay? If we want to compare them, which one is better and which one is, again, this is just some ways of steganography, similar in addition to the ones that we mentioned. So that falls under things like you write a complete message and then very hidden dots are there to tell the intended receiver, who should be looking for those dots, which letters to pick, and all the other statements are irrelevant, right? And those letters are going to compose a particular message. Or using invisible ink. We have seen that in some espionage movies and series and stuff like that, right? Or pin punctures. So you just puncture parts of the paper, and then the person who's looking for the message is going to raise that against some light, and then they see those punctures as some text. Or typewriter correction, which is a white on white. So you write using white color. The typewriter correction ribbon is just a white color. And if you write that on a white paper, nobody's going to be able to read it unless someone is going to use that against some reflection light and try to move it one way or the other until they see the luminance of that white color and they start reading it, whatever. The idea, again, regardless of the caricature and actual implementation, but the idea here is that the philosophy of steganography is that your method is not complicated. Your method is simply relying on hiding your actual information under some irrelevant information, some camouflage, right? such that the attacker doesn't know if there is something in the first place, right? But if the attacker knows, breaking that system is going to be very easy.
So we
Okay.
can merge them, right?
Of course you can, okay? On the other side, cryptography is not done this way. The attacker knows that there is something, and it is important because it's encrypted, but because you use some complicated methods, it's very difficult for the attacker to retrieve the original message, okay? If you compare those two approaches, there are pros and cons to each one of them, and as you suggested, we might even use a combination of them. But the main advantages and disadvantages of those two methods are listed in like one more or less this very simple slide, okay? For steganography, major disadvantage are two things. Number one, the rate of transmission is very little because you have to add a lot of stuff around your message, right? Which means these stuff are gonna consume your power of transmission if you are talking about wireless communication system, which what we care about here. And it's gonna consume your bandwidth, your available channel width rate of transmission, right? So you'll end up with very low rate of transmission of the actual information. You might be transmitting a lot of bits, but the actual information are very little among those bits going through the channel. And the second problem is, as I mentioned, if the attacker knows that this particular part of transmission has some hidden message, because the protection is not really that strong, he or she can apply certain statistical method and certain random approaches, and then they can eventually retrieve your message very quickly. So the main protection comes from the fact that you are hiding the fact that there is a message from the attacker. You are not really protecting the message itself, just hiding the fact that there is some important message going over the channel at that point. If that's discovered, your system will break down. Now, if we go to the encryption, it's the other way around, right? The fact that there is something that the attacker is aware about encourages them to perform lots of analysis and so on. So that's a disadvantage to that system, right? The encryption method, because the attacker knows that there is something of importance, so they will keep attacking and trying, okay? On the other side, if you do some good design for your encryption system, you can achieve very reasonable rate of transmission. So that's the advantage of the encryption method, okay? It's a little bit more complicated, of course, so it requires a little bit more sophisticated devices to perform encryption and decryption, but still the rate that you achieve outweighs the cost that you have to pay for the encryption system. Any questions? We are not gonna do steganography here. One of the most famous ways of doing steganography in a practical way is hiding text inside images. So you have an image that looks like a natural scene or a picture of someone, and then there is small arrangement of pixels inside that, which are actually representing some text. Cannot be seen by an eye which is not expecting that's there, okay? But if someone is expecting and searching for it with a particular guide, they can actually see it, okay? That's one very famous method of steganography.
It needs a high rate, though, right? It needs a high rate to...
You need a high rate to send the image, but the actual information that you send ends up being very, very low rate information. Most of your bandwidth or rate of communication is consumed for the other irrelevant information. Yeah. Okay. Okay, done with this part.